we're taking the terms of the sequences that we talked about in 11.1 and we are going to add them together, which gives us the sum from n equal 1 to infinity of the terms a sub n. Now, this is adding an infinite number of terms, which you might wonder, if you add an infinite number of terms, does it get larger and larger and larger if you keep adding all those terms together? And the answer is that maybe or maybe not. This sum may be actually approaching some number. Okay? So in order to decide if this actually has a sum or if it just gets larger and larger and larger, what we do is we look at a sequence of partial sums. So what we look at is the first term, the sum of the first term, which is just the first term. We look at S sub 2, which is the sum of the first two terms. Then we look at what happens if we add three terms together. And we're looking at these totals out here. Are these totals getting larger and larger and larger, or are these totals getting closer to another number? So we keep going forever. And again, we're looking at this sequence of numbers, and we're looking to see if that approaches some kind of sum. Okay? If it approaches a number, then we say that the sequence converges. Excuse me, we say the series converges. If this sequence of numbers approaches a particular number, we say that the series converges. If this particular list of numbers right here gets larger and larger and larger, then we say that it diverges. Correct, correct. Yeah, and sometimes these terms alternate between positives and negatives. So if you've got a plus and a minus and a plus and a minus and a plus and a minus, yeah, what's happening to it? Is it, is it still getting closer and closer to some number, or is it getting bigger and bigger, or smaller and smaller? What's happening to that list of numbers?
So you're saying that the SN is like it's basically going to infinity?
It could.
What about negative infinity?
It could. It certainly could. Or it could approach 1, or it could approach 1/2, or it could approach, a decimal. It could approach something, or it could get larger. It's just no telling what happens. And that's kind of what we're going to be looking at for the rest of the chapter, or at least the rest half of the chapter. We're going to be looking at different types of series, and we're going to be trying to decide if the series converge or diverge. Now I'm just going to take a series like this, series from n equal 1 to infinity of 1 over n squared plus 1, and kind of give you an idea of what we do, or what this thing is talking about. All right, first I'm going to list the first few terms, A1, A2, A3, A4, A5. All right, these are the terms. This is my A sub n right here. A sub n is 1 over n squared plus 1. If I put 1 where n is, then this is going to give me the fraction 1/2. If I put 2 in here, that's going to be 1/5. If I put 3 in there, that's 1/10. If I put 4 right there, I think that's 1/17. If I put 5 right there, that's 1 over 26. The next one would be 1 over 37. And these fractions look like they're getting smaller and smaller and smaller. In fact, if I looked at these fractions, these terms of the sequence, these would be going, if this is 1, these would be going, if this is 1, 2, 3, 4, 5, 6. If this is my n-axis down here, the first term is 1/2, the next one is 1/5, the next one is 1/10, the next one is 1 over 17, 1 over 26, 1 over 37. It looks like the terms of the sequence are approaching 0 is what that looks like to me. But that doesn't tell us about the sum. What if we take these and start adding them together? If we look at S sub 1, which is just the first term, that's 1/2. If we look at S sub 2, then you're adding those two together. You have 1/2 plus 1/5, which I believe would be 7 over 10. If you take S sub 3, then you're adding the first three terms together. So you take 7 over 10 plus 1 over 10, and that looks like 8 over 10. And then S4 is going to be the 8 over 10 plus the 1 over 17, and I don't know what that is. So 8 divided by 10 plus 1 divided by 17. You get 7. I got 73 over 85. S sub 5 is going to be the 73 over 85 plus the 1 over 26. Ooh. Which is 1,983 divided by 2210. And if I was going to have to graph these, I would probably start changing these to decimals to look at. The next term, S sub 6, is going to be this one plus the 1 over 37. So it's S sub 5 plus 1 over 37. Oh yeah, this is a large 75581 over 81770. And if I had to guess, if I change these to decimals, I am guessing that these look like they're 0.9 something. I would be guessing that these would be getting closer and closer to 1 is what I would guess. So I would guess, just by looking at these numbers, that this sum is getting closer and closer to 1. So it would be approaching 1. Okay? So that's what I mean. The terms went to 0, but the sum is actually going closer and closer to 1. And we're looking at the sum. All right, question about what I did for that. I would say this one is convergent, and that it converges to 1. And that's just a guess. It may or may not go to 1. And I'm only looking at 6 terms, you know. I mean, if you're going to infinity, you're adding an infinite number of terms. It may actually be a little bit more than 1, but it just looks right now like it's going to 1. And that's the best I can do is look at it. All right, well, as you might guess, this might be pretty tedious if you had to do this for every series that was out there. Exactly. So there are other ways to tell whether a series is convergent or divergent, and that is by looking at the type of series that you have. So now I'm going to talk about a few of the important types of series that you have. All right, the first type of series that's an important is geometric. All right, a geometric series. This is a series where each term is, you get the next term by multiplying something by the term in front of it. For instance, if I have the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32 plus ... Right, this is a geometric series because I'm multiplying 1/2 times every term to get the next one. 1/2 times 1 is 1/2. 1/2 times 1/2 is 1/4. 1/2 times 1/4 is 1/8. I'm multiplying by 1/2, which that is what we call our common ratio. common ratio. The general form for a geometric series is a series from n equal 1 to infinity of a r to the n minus 1. And you don't have to put the r in parentheses. A is a constant. It is not equal to 0. This r is our common ratio. And A is just any constant. Now the thing about a geometric series is it will converge for some values and it will diverge for others. If the absolute value of your common ratio is less than 1, this series converges. And if it converges, it has a sum. And the formula for the sum is the first term divided by 1 minus your common ratio. If it converges, it will have a sum. This is the formula for finding the sum. Now the book writes this formula as A over 1 minus R. That's fine as long as you realize that A is the first term. If the absolute value of the common ratio is greater than or equal to 1, a geometric series diverges. All right, so I want to go back to my problem right up here, the one that I wrote up here, this geometric series. Oh, yeah, sure.
Where you set up your summations right there.
Yeah.
Is that going to apply, do you use that to test the all the geometry, or is that just for this one specific problem?
All of them.
You'll test it for just the geometry.
If you have a series that is geometric in form, this is what you do. You look for the R, the absolute value of R.
But the summation part, that's what you use to test it.
Yes. I guess I'm answering you right. All right. You'll know in a minute if I answered you right.
Kind of like a formula part.
Yeah, it's a formula for geometric series, yes. All right, so I want to go back over here to this one, the one that I wrote. I didn't give you a formula for it, but you quickly told me that the common ratio is 1/2. So to decide if this series converges or diverges, all I have to do is look at this common ratio. The absolute value of 1/2 is 1/2. 1/2 is less than 1. So just by this formula right here, this series that I wrote here is going to converge because my common ratio is less than 1. And I can find the sum of this series by using this formula right here. The sum of this series is my first term, which is 1, over 1 minus my common ratio, which is 1/2. So the sum of this series is 1 minus 1/2, which is 1/2. 1 divided by 1/2 is 2. It looks like the sum of my series is going to be 2.
So is that where it converges to?
Yes. If I keep adding up all these terms together, I'm going to keep getting closer and closer and closer to 2. The more terms I add up there, the closer I'm getting to 2. Okay, that's sort of halfway with me.
Now, 1 minus that being the sum of basically the first term over 1 minus R.
First term over 1 minus r. Exactly. First term over 1 minus r, and that's how you find your sum. If it diverges, it does not have a sum. Okay? If it diverges, there is no sum. It's going to infinity, it's going to negative infinity, or it's just going back and forth all over the place.
Does it never kind of just go in the same area on the line?
Right. All right, number 19 in your book. They list this series of numbers. 10 minus 2 plus 0.4 minus 0.08 plus ... They tell you it is a geometric series. So it has a common ratio. If you can't see it, I can tell you.
You want this?
I was going to say, Okay.
It's all the same.
Obviously you can see it. For those that can't see it, take one term, divide it by the one in front of it. So it doesn't matter which term you take. So if you take the 0.4 and divide it by -2, and you said I'm going to get -1/5. That is your common ratio. Okay? I need to look at the absolute value of that to decide if this is going to converge or diverge. The absolute value of this is 1/5, which happens to be less than 1, therefore it converges. And if it converges, it's got a sum. So the sum is the first term, right, divided by 1 minus the common ratio. So it's 1 minus -1/5. So that's 1 plus 1/5. What is that going to be, that sum? Is it? 10. How about 25 over 3? How about 25 over 3? Make sure you put the denominator in parentheses.
Well, you got it. Actually, you might have to agree with that one.
That wouldn't matter on this one. All right, number 24. They give us a formula. Sum from, now you're getting the 25 over 3?
25 over 6. Let me know. One more time. 4, 5, 3, 4, 5.
No, 6/5. Minus a minus is plus.
Oh, that's right. That would be the problem.
Okay. All right. This is a geometric series. This geometric series is not really in the proper form because I've got 3 to the n plus 1 here. I've got the denominator is to the nth power. I need something to the same power. It can be n minus 1. It can be n. It can be n plus 1. It just has to be something to the same power. So what I do for this is I take this and do algebra. 3 to the n plus 1 is the same thing as 3 to the n times 3 to the first. Remember, if you multiply, the bases are the same, you add your exponents. Divided by -2 to the n. These two things are to the same power. So this is the sum from n equals 0 to infinity of -3/2 to the nth power times 3. All right, did y'all follow my algebra through here? All right, now that I'm in this form, this is my common ratio. This is my R. So the absolute value of -3/2 is +3/2. That is bigger than 1. If the absolute value of R is bigger than 1, my series diverges. And it has no sum. By the way, on WebAssign, if it says write diverges, if it has it all capital letters, put it all capital letters or it will count it wrong. It will tell you it's wrong. So, and I think they want all capital letters. All right. Go good? All right, what if I have one like this, 31? Trying to get all my geometric series out of the way for a minute. This is n equal 1 to infinity. 3 to the n plus 1 times 4 to the -n. Oops. All right, you're again going to have to do some algebra to get your common ratio. So the negative exponent, n equal 1 to infinity. This is 3 to the n plus 1 over 4 to the n. Make your exponent positive. Then you can do some algebra, right? You're going to pull a 3 out. I'll go ahead and write all the steps. So that's going to be the series from n equal 1 to infinity, 3 times 3/4 to the n.
The only thing you did was negative n, just put it underlined.
Right, I made that positive, right, put it on the bottom. And this is now my common ratio. So the absolute value of 3/4 is obviously 3/4, which is less than 1, so this is going to converge. If it converges, it has a sum. All right, the sum is the first term divided by 1 minus r. How do I find the first term of this series? I take this number right here, n equal 1, and I put it right here. So this is 3/4 to the first power times 3, which looks like it's going to be 9/4. So 9/4 over 1 minus my common ratio, which is 3/4. So is that going to be 9 maybe? So my sum is 9. Okay? Now, I have not gotten to the rules for sequences and series, but I can do this problem and explain it to you. This is 32. Sum from n equal 1 to infinity, negative 0.2 to the n plus 0.6 to the n minus 1. They want to know if this series converges or diverges. All right, well, the rules for sequences and series, the properties are on page 754. But there's a property that says if you are adding two things, taking the sum of this is the same thing as the sum, you split it up. N equal 1 to infinity of negative 0.2 to the n plus the series from n equal 1 to infinity of 0.6 to the n minus 1. You split this in two. Now, for this to converge, they both have to converge. If one of these diverges, then the whole thing diverges. Okay, you following? It's an all or nothing deal. We did that when we were doing improper intervals. All right, so for this one, this is geometric. This is your R. So the absolute value of your common ratio is 0.2, which is less than 1. This one converges. The R for the other one is 0.6, which is also less than 1. This one converges. Since these both converge, the whole thing converges.
You got to find
The sum.
separate.
Exactly. So now you find the sum of the first one plus the sum of the second one. You add them together to get your total sum. Do you want me to go through and do it? Yes? All right, the sum of the first one, S sub 1, is the first term. What is the first term of this sequence going to be? Positive or negative? Negative. Negative 0.2 divided by 1 minus your common ratio, which is negative 0.2. R is negative. So, excuse me, whatever this is. I think I got negative 1/6. Y'all better check me. The sum of the second one. Did you get 1/6? Y'all get negative 1/6 in this one? Okay. Well, if you find something different in a minute, let me know. All right. On the second one, the first term. This is 0. This is 0.6 to the 0 power, which is 1. First term is 1 over 1 minus your common ratio, which is 0.6. And I believe I got 5/3 on that one. So the total sum is negative 1/6 plus 5/3. Which looks like it's 3/2.
So when we're writing our answer, do you want to put all that together, converge it at 3/2, or you just like that?
This is fine. This is fine. All right. Now remember, if one of these had diverged, like if this had been 1.6 right there, this one would have diverged because this is bigger than 1, so the whole thing would diverge. Okay. Did y'all find a mistake of mine? This one? This one? Oh, I put multiply. Yeah, I typed it in wrong. I typed in, my denominator was wrong. 5/2. Which makes my total sum what? Big difference. Okay, thanks. Is that right now? Okay, thanks. Yeah, I definitely typed this in wrong. All right, so this is a geometric series. All right, another type of series is something called harmonic series.
Is that a negative? No.
I have negative 1/6. Yeah, that's right. All right, harmonic series. Series from n equal 1 to infinity of 1 over n. So this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus dot 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 plus 1 over n plus dot 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 dot.
Is that 1 over n or 1 over n?
That's an n.
No, I'm sure it's fine.
Yeah, that's an n. And this is an n. All right, this is the harmonic series. This one always diverges. So if you recognize a harmonic series or a multiple of the harmonic series, it will diverge. That's another one of those properties. So, sequence from n equal 1 to infinity of 3 over n. This is 3 times the harmonic series. So it diverges. You don't have to do any work. It just diverges because it is a multiple of the harmonic. Because it's harmonic.
So it don't matter, no matter what, that's above that n, it's going to be harmonic, no matter what.
It's going to be a multiple of the harmonic series, and it's still going to diverge.
But as long as you know that it's the infinity n equals 1, any number over it's going to be harmonic.
Right.
Like that.
Or that. If it's 1 over 100 n. This is still a multiple of your harmonic because it's 1 over 100 times 1 over n. This is harmonic. The 1 over 100 comes out in the front. It is still divergent because it is a multiple of your harmonic series. Okay, so if you can recognize that, it makes life easy. At least it does in my book. Okay? Now, there are some other theorems in here that you need to be aware of. One of them is the fact that if a series, let's see, where is this one? Theorem 6 on page 753. If the series from n equal 1 to infinity of a sub n is convergent, then the limit as n approaches infinity of a sub n will be equal to 0. This does not say, and I cannot caution you enough, this does not say that if the limit is 0, it is convergent. It says if it's convergent, the limit would be 0. And I can take this one as for an example right here. If you look at this harmonic series from n equal 1 to infinity of 1 over n, and if you look at the limit as n approaches infinity of 1 over n, what is that limit? This limit is 0. But what do you know about the harmonic series? It diverges. So you cannot go backwards on this one, okay? The converse is not true, so please don't ever try to use it. But what it does say is if a series is convergent, then the limit's going to be 0. And then the theorem right below that, which is called the test for divergence. Notice this test for divergence, it does not test for convergence. If you want to see if a series is divergent, you can use this test. And the test says, if the limit as n approaches infinity of a sub n, if it is not 0, or it does not exist. If it is not 0, or it does not exist, then the series from n equal 1 to infinity is divergent. Yeah.
In the book it says note 2 right below theorem 6. Is that what you're going to highlight that?
Yes, highlight note 2. Converse of theorem 6 is not true. If the limit equals 0, you cannot conclude a series is convergent at all. All right, which is the same thing as this. All right, notice, do you see anything in here about the limit equaling 0? What happens if the limit equals 0? No. This will test for divergence. If you take the limit of a series and you see that it's not 0 or it doesn't exist, then you can say the series is divergent. If it's equal to 0, you don't know anything. Because this one was equal to 0. The limit of this one is equal to 0. It's not convergent, it's divergent. It's just you don't know anything, okay? All right, now let me show you, see if I can find something with that in it. I don't see anything right now. But these are theorems that you'll be using. By the way, all these theorems, the geometric, the harmonic, the test for divergence, these are things that we're going to be using all the whole chapter. So kind of collect those in a little place and keep them with you as you go to each chapter or each section ahead of us, okay? Okay, the last thing that I want to do, and this actually involves, I meant to do it when I was doing geometric series, this involves taking a decimal and changing it back to a fraction. We're going to treat it as a geometric series. For instance, this isn't, yeah, this is for geometric. All right, if I have, let's do this one. This is number 52. The decimal, 4, 6, 4, 6, 4, 6, blah, 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 blah. It repeats 4 6s forever. They want me to write this as a ratio of integers. So I'm changing it back to a fraction. So what I'm going to do is treat this as a geometric series. All right, the part that repeats is the 4, 6. So I'm going to write this as a series of fractions. This is 46 over 10 squared. That's the hundredths place. Plus 46 over 10 to the 4th. I'm moving out 4 decimal places. Plus 46 over 10 to the 6th. Plus dot, 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 dot. You can go ahead and show it. 46 times 10 to the 8. I divided by 10 to the 8. You're moving out 2 decimal places every time. Everybody see how I'm getting these fractions? All right, this is geometric. There is a common ratio. So find your common ratio. What am I multiplying times this one? What am I multiplying times this to get to this one? Or times this to get to this one? 1 over what? 1 over 100 or 1 over 10 squared, whichever way you see it. 1 over 100, 1 over 10 squared. That is your common ratio. That's your R. So to find the sum of this series, that's what we're actually looking at. You take the first term, 46 over 10 squared, divided by 1 minus your common ratio, which is 1 over 10 squared. You may put that in your calculator and it will give you a fraction, which is what they are looking for. 46 divided by 10 to the 2nd, divided by, well, and this is 46 over 99, which is probably what you thought it was anyway, but that's how you get it. Let me do one that may not be quite as easy. 1.23456 and the 567 repeats. Now you probably can't get this one to me off the top of your head. Probably not. No, you can. I can't. All right. So what you do? Break it into a bunch of fractions. This is a whole number 1. Plus, I would take the 234 over 10, I went out 3 places, 10 to the 3rd. Plus, all right, here's the part that repeats, the 567. 567 over 10, what place am I out to here? The 6. When I do the next 567, what is it going to be? 10 to the what? Which one? 9th. Plus dot, 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 dot. The part that repeats is the geometric part. This is the geometric part. So this is where you're looking for your common ratio, or your R. What am I multiplying times the first one? How did I get to that second term? How did I go from here to here? I went from 10 to the 6th to 10 to the 9th. I'm doing 10 to the 3rd. Or 1 over 1,000. That's my common ratio. So to find the sum of this geometric part, you take the first term, which is 567 over 10 to the 6th, divided by 1 minus 1 over 10 to the 3rd. And get that sum. Whoops. If I put that in my calculator, I got 21 over 37,000. Did y'all get that? Y'all didn't? Oh. Oh, okay. We're not finished. We're not finished. Because we got to go back and add these two to this one. So now you go back and add 1 plus 234 over 10 to the third plus 21 over 37,000. Add those all together. And I got 45679 divided by 37,000. Did y'all get that? Nope. That's what I got, and I'm gonna check it. That's right. And when I checked it, that's what I got. So that is the fraction for that decimal, that repeating decimal.